Let's go. Welcome. We have for a speaker one more new professor at our department. It is Minghong Fang. I hope I pronounce correctly. He is a tenure-track assistant professor at our department. He was postdoctoral associate at Department of Electrical and Computer Engineering at Duke University from 2022 to 24. He earned his PhD at at the Department of Electrical and Computer Engineering, Ohio State University. In 22, his research interests are in machine learning, security, privacy, recent focus on intersection of these disciplines. Interested in distributed optimization for learning and networking. Research has been published in top-tier security, machine learning, and networking venues. There is a lot of list of these venues. I will not even enumerate all of them. Maybe the most important is his Eugenic Security 2020 paper was recognized as one of the top normalized top 100 security papers since, oh my gosh, 1981. That's really for a long period. And also received 2024 IFIP IEEE Networking Best Paper Runner-Up Award. So a lot of these very recognized recognitions. And today's talk is about towards secure federated learning. Welcome at UFL, and welcome for today's presentation. Please, let's go with the talk. Thank you.
Okay, thank you. Thank you for the introduction. I'm happy to be here to meet with you and to share my research. The talk is about the secure and federated learning. I think everyone here in the last decade has witnessed the progress of machine learning. Machine learning is changing the world and has so many valuable applications, from smaller things like sensor automation to large-scale connectivity environment like smart city. Machine learning has so many amazing applications, and these applications are constantly generating a huge amount of data. As we can see from this figure, the amount of data generated every year increases exponentially. It is time to say we are in the era of big data. The rapid growth of large diverse data sets enables machine learning models to make photo generalizations across different domains. So this is important to develop machine learning models that are robust and can be adapted to different scenarios where the data can differ significantly. The success of machine learning models heavily depend on the availability of a large amount of data. However, such large-scale data are often distributed across different locations. So the traditional way to address this challenge is centralized learning, which means all the data are moved to a single location. So this is a standard centralized learning. So as you may know, centralized learning is the popular conventional machine learning paradigm. Suppose we are given some class. This class could be smartphone, IoT devices, or self-driving cars. Each class has some local training data. In centralized learning, this class sends the raw training data to a cloud server, which is managed by a service provider such as Google, Facebook, and Apple. The service provider then uses a class raw training data to train a machine learning model. And the model is used to provide service for the class. So this is a standard pipeline for centralized machine learning. However, such centralized learning has multiple challenges. The first challenge is that centralized learning is vulnerable to data linkage because private data cannot be shared among the class. For example, a a single hospital may not be able to train a high quality model because it does not have enough training data. Ideally, hospitals can benefit more if they can jointly train a machine learning model on the unit of the training data. However, the data cannot be shared because the patient's data is private by nature. So this is one limitation of centralized learning because of the privacy issues. Anonymization techniques such as differential privacy have been proposed to reduce this risk. However, this method can make it hard to balance privacy protection and model performance. The second challenge is that centralized learning involves high communication costs, which may be intolerable for resource-constrained clients. And these clients often run environments with limited bandwidth, so it is hard or even infeasible to transmit large amount of data to the central server. So this is the second challenge for centralized learning. So federated learning is a lower machine learning approach to address the challenge in centralized learning. The key idea is that we offload the training process to the class. So in particular, in federated learning, class raw training data stay locally on themselves. Each client trains a local machine learning model and sends its local machine learning model to the server. The server then combines the class local models to get a new global model. So here I only provide a high-level idea of federated learning. The pipeline of federated learning will be introduced in later slides. So federated learning is a private approach in industry and a promising research topic in academia. So as we can see in this figure, the market size of federated learning is growing with annual growth rate of more than 11%, with applications spanning different domains, such as the Internet of Things, bioinformatics, finance, healthcare, and many others. Additionally, federated learning remains one of the popular topics in recent machine learning conferences. So consequently, people have high hopes for federated learning, and it becomes one of the mainstream learning paradigm. Federated learning is a new way of using data and has received a lot of attention in recent years. So imagine federated learning as an iceberg. Most research, as you can see above the water, has focused on improving the accuracy and the performance in federated learning. However, there is a large part of iceberg under the water, namely the security issues is not receiving enough attention. This problem could make federated learning unsafe if they are not fixed. So identifying and addressing these security vulnerabilities is a key step to developing robust and reliable machine learning systems. Security is a critical challenge in this decentralized architecture. A recent report by Facebook indicates that these decentralized settings are vulnerable to point attack and hardware failures. Additionally, researchers highlight in a recent book that federated learning may introduce new attack service and the training time. So security is a critical challenge in federated learning. So today I will discuss the following two questions. The first question is, what are the security issues in federated learning? After understanding the security issues in federated learning, I will discuss the second question, how to build secure federated learning to address the security issues. And this is the flow of today's talk. First, I want to introduce federated learning in detail and explain why federated learning is vulnerable to point attack. Then I want to discuss state-of-the-art Bayesian robust method. Next, I will show that existing Bayesian robust methods are actually not robust. In fact, they are still vulnerable to our proposed local model point attack. Following that, I will discuss how to defend against our proposed local model point attack. The first four topics will be covered in part 1, and I want to introduce our defense in part 2. So this is the flow of today's talk. Okay, so let's go to part one. So basically, most of the time we can write our machine learning program as this minimization program. So we want to minimize our objective function that can be decomposed as a sum of n components. Here n is the number of clans, W is the machine learning model, or we call model parameter. So every clan has its own local training objective and local training data. Here, class i's training data is sampled from DI, where Fi is the training objective for clan I. So in federated learning, we are able to jointly find the common model W that works well on all clans. So this is the objective in federated learning. So here I want to formally introduce the federated learning and background. So suppose we are given some clans. Each clan has some local training data. We also have a cloud server. The server maintains a machine learning model, which we call global model. Each clan also maintains a machine learning model, which we call local model. Federated learning is a repetitive procedure, and in each training round, federated learning performs the following 3 steps. In step 1, the server sends the current global model to all clans or subset of clans. In step 2, the clans train their local models based on the current global model and the local training data. For example, clan I first initializes local model WI as a current global model W. Then clan I uses a stochastic rate descent to update its local model. Here alpha is learning rate, GI is a grading. Then the clans send a local model to the central server. In step 3, the server aggregates the clans' local models to get a new global model. So for example, in Fed average proposed by Google, the global model W is basically the average of class local models. So federated learning basically repeats the 3 steps for many training rounds, and the final global model is used to provide service for the class. So this is a standard pipeline for federated learning. So we also know that in step 2, it is equivalent to send a local model update to the central server. Here, local model update is a difference between the updated local model and the current global model. Federated learning is basically a distributed system, and due to its distributed nature, it is fundamentally vulnerable to point attack. An attacker may have access to some malicious clans. These malicious clans could be fake clans injected by attacker or existing blind clans compromised by attacker, such as by malware infection. A malicious clan can poison its local training data, which is known as data point attack. So, for example, label flipping attack is one kind of data point attack, where the attacker flips the labels of local training data on the malicious clans. For example, for this training example, the attacker flips the label from the dog to the cat. So this is label flipping attack. It is one kind of the data point attack. A malicious clan can also directly poison its local model, which we call local model point attack. So Gauss attack is one kind of local model point attack, where the attacker adds random Gauss noise to the local model WI, and the point the local model WI prime is sent to the server. So this is a local model point attack, where the attacker directly modifies the local models on the malicious class. And eventually, the global model is poisoned, and the poisoned global model makes incorrect prediction as attack design. So this is what we call Byzantine setting, which means some class may have some adversarial or bad behavior. So this is a definition of Byzantine attack. To defend against this point attack, such as label flipping attack and DOS attack, the machine learning community has proposed multiple Byzantine robust methods, and this Byzantine robust method actually uses the Byzantine robust aggregation rule to aggregate the local models submitted by the class. For example, in this case, the server used the aggregation rule A to combine the class local models W1 to Wn. Here A could be the chrome, trade mean, and median. So roughly speaking, the key idea of this Byzantine robust method is to remove the outlier before aggregating them. Under some assumptions, for example, the class local training data are independent and identical distributed, and the load function is smooth. This Byzantine robust method can even bound the change of global model parameters caused by the malicious class. So which means this Byzantine robust method even provides some several guarantees under some assumptions. So here I want to use median as one example to illustrate Byzantine robust aggregation rule. Suppose each local or global model has m parameters. These are m parameters of class 1's local model. These are m parameters of class 2's local model. These are m parameters of class n's local model. The server aggregate these n local models to get a new global model. For example, the server computes the first parameter of the global model by taking the median of the first parameter of n local models. The server computes the second parameter of the global model by taking the median of the second parameter of the n local model. And repeat this procedure until compute the m parameters of the global models. So this is how the median aggregate the class local models. So our research shows that existing Byzantine robust methods such as chrome, trade mean, and median are still vulnerable to our proposed local model point attack. So in particular, the attacker can substantially increase the testing error rate of the global model learned by this Byzantine robust method. Here, testing error rate is the error rate of the global model on the testing dataset. So this work was significant in shifting the focus of the research community. Before our study, the main emphasis was on improving the accuracy and reducing the communication costs in federated learning, with little attention to the security concerns. So by highlighting the fundamental vulnerabilities in federated learning, our research opened up new research direction and has motivated many researchers to further explore the security challenges in federated learning. So here I want to use this flow again to better illustrate the relationship between our attack and existing research. Federated learning is vulnerable to point attack. To defend against this point attack, the machine learning community has proposed multiple Byzantine robust methods such as crawl, trade mean, and median. However, when challenging the existing understandings, we demonstrated that the current methods were not as robust as believed. So we basically attacked the existing defense. So this is our major contribution. We consider the following threat model in our attack. The attacker's goal is to increase the testing error rate of the global model. The attacker wants the testing error rate as large as possible. So the larger the testing error rate, the better the attack performance. Attacker may have access to some malicious class, which could be fake class injected by attacker or existing belong class compromised by attacker. And this malicious class could send arbitrary local models to the central server. So in terms of attacker's knowledge, we consider both full knowledge attack and partial knowledge attack. In the full knowledge attack, we assume that attacker knows the local models on all class. For example, in this case, we have 3 classes. In the full knowledge attack, we assume the attacker knows the local models on all 3 classes. In the partial knowledge attack, we assume that attacker only knows the local models on the malicious class. For example, if the first class is a malicious class, the last 2 are belong class. So in the partial knowledge attack, we assume that attacker only knows the local models on the malicious class. The attacker may or may not know the aggregation rule used by the server. So in our environment, so when the attacker does not know the aggregation rule used by a server, the attacker can just assume one aggregation rule. So this is also called the transferability of our attack. So next, I want to use a few slides to introduce the key idea of our attack. So suppose W pivot is the global model in the pivot training run. And for simplicity, we assume we only have 2 classes. W1 is a local model on client 1. W2 is a local model on client 2 in the current training run. These 2 local models are sent to the server. The server combine W1 and W2 to get a new global model W. So with our low attack, the global model move along some directions like this in 2 consecutive training runs, which means the global model moves from W pivot to W on the low attack. So the key idea of our attack is to deviate the global model the most along the inverse of the direction before attack. So for example, in this case, we aim to deviate the global model W to be W prime. So let's assume client 1 is malicious, and in order to deviate the global model to be W prime, client 1 sends a poisoned local model W1 prime to the central server, such that the aggregation of W1 prime and W2 becomes W prime. So this is the key idea of our attack. So we formulate our attack as this optimization program. So the objective of the attacker is to maximize the deviation of the global model. Here, W is the global model before attack. W prime is the global model after attack. S is the updated direction of the global model before attack, which is computed as a sine of W minus W pairs. So we assume we have N class, and the first C class are malicious. So W1 prime, W2 prime to WC prime are the points and local models on the malicious class. So our optimization program aims to find the optimal points and local models on the malicious class in order to maximize the deviation of the global model. Here A is the aggregation rule used by the server, such as prone, trim mean, and median. So we also know that here the deviation has 2 meanings. First, the attacker wants to deviate the magnitude of W prime, which means the L2 long of W prime, because this is a vector. And also, the attacker also wants to deviate the direction of the global model. So this is objective of the attacker. So in our attack, attacker basically solves this optimization problem in multiple training runs. And in every training run, the attacker maximizes the deviation of the global model. After some runs, the deviation will be accumulated. We also know that our formulation is applicable to any execution rule. So in the future, if we propose a new execution rule, we can use this attack framework to evaluate its robustness. So this is the formulation of our attack. So in our experiment, so by default, we assume there are 100 classes in total, and 20 of them are malicious. We evaluate our attack on multiple data sets from different domains, such as MList, Flash MList, C10, and human activity regularization dataset. So note that the human activity regularization dataset is a well-worn dataset that aims to regularize human activities, and this dataset is collected from the smartphone users. So in federated learning, so one unique feature is that class training data are often not independent and identical distributed. So in our experiment, we allocate the dataset to the class such that the class local training data are long ID distributed. So the detail of the long ID can be seen in our paper. So this table shows the results of our attack and multiple baseline attacks. So each row means a Byzantine robust method. So this column means all class are benign, which means there are low malicious class in the system. This column means the attacker adds random Gauss noise to the local models on the malicious class. This column means the attacker flips the labels of local training data on the malicious class. So recall that label flipping attack is one kind of data pooling attack. This column means our attack in the partial noise setting. So this value means the attacker corrupts the malicious local models based on the Chrome execution rule, and the attacker only loads the local models on the malicious class. This value means the attacker corrupts the malicious local models based on the tripling execution rule, and the attacker only loads the local models on the malicious class. This column means our attack in the full noise setting, which means the attacker loads the local models on all class. The number in the table are the testing error rate of the global model. So from the attacker perspective, the larger the testing error rate, the better the attack performance. As we can see that our attack can substantially increase the testing error rate of the global model learned by different Byzantine robust method. So this figure shows the impact of fraction of malicious class on the attack. So here the x-axis is a fraction of malicious class. The y-axis is a testing error rate of the global model. And different curve means a different attack. And we can see that our attack are more effective when more classes are malicious. This figure shows the impact of degree of long ID on the class training data. So the x-axis is a degree of long ID. The y-axis is a testing error rate of the global model. And again, different curve means a different attack. So as we can see from this figure, our attack are more effective when the class local training data are more long ID. So the reason is that when the class training data are highly heterogeneous, even belong class local model differs significantly. Therefore, it is hard for the server to distinguish the benign local models from the malicious ones. This table compares our local model point attack with the state-of-the-art data point attack. So recall that data point attack aims to poison the local training data on the malicious class, while our attack poison the local models on the malicious class. This column means all classes are benign and there are no malicious class in the system. This column is the state-of-the-art data point attack, where the attacker aims to poison the features of local training data on the malicious class. We can see that this data point attack is different from the label flipping attack. So for label flipping attack, the attacker flips the labels of local training data. However, for this data point attack, the attacker changes the features of the local training data on the malicious class. The last two column our attack in the partial and full notice setting. So each row means a binary advanced method. Again, the number in the table are the testing error rate of the global model. As we can see from this table, data point attacks are not effective for binary advanced method because this first two columns have both the same testing error rate. However, our attack are effective. We can see that we can substantially increase the testing error rate of different binary advanced methods. So to summarize a little bit, we propose a general framework to attack the binary advanced and federated learning. Our result shows that existing binary advanced methods are still vulnerable to local model point attack, which means these defenses are actually not robust. We can still attack this defense method. So this is part one of today's talk. Okay, I want to stop here for a few seconds. Okay, so from part one, we say that existing binary advanced methods are actually not robust. They are still vulnerable to our proposed local model point attack. So one open question arises: can we defend against our proposed local model point attack? So in the following, I will show the answer to that question is yes. So in particular, in part two, I will demonstrate that we can build scale federated learning to reduce the impact of our proposed local model point attack, which means this is our defense. We use this defense to reduce the impact of our attack. So first, the root cause of insecurity in federated learning is that there is low load of trust in the system. So which means from the server perspective, every client could be malicious. For example, if we have n clients, so from the server perspective, this n client could be malicious. So based on this observation, we propose to build scale federated learning by bootstrapping trust on the server. So in our proposed ever trust, the server collects a small and clean training data set. The server maintains a local model based on this collected training data set. It's just like how client maintains a local model. We call the server's local model as a server model. Then the server uses the server model update to bootstrap trust. In particular, in each training run, the server assigns trust scores to the class based on the similarities between the class local model updates and server model updates. Then the server aggregates the class local model updates to get a new global model updates based on the class trust scores. So this is a key idea of our effort trust. So recall that in federated learning, in each training run, we have 3 steps. So in step 1, the server sends the current global model to all clans or subset of clans. In step 2, the clans send the local models. In step 2, the clans train the local models based on the current global model and the local training data. So however, unlike what we did in part 1, now we assume the clan sends the local model updates to the central server. For example, the class first compute the local model updates delta W as a difference between the updated local model and the current global model. Then the class sends the local model updates delta W to the central server. In step 3, the server aggregates the class local models to get a new global model updates, and further use the global model updates to update the global model. So here we basically design a new binary mask evaluation rule in step 3 of Federated framework. The key idea of our trust is that from the server perspective, every client should be malicious. So the server class a small training data set or validation data set. The server compute a server mode update based on this small validation data set. When the server receives a local mode update from any client, the server uses this server mode update to check whether the received local mode update is malicious or benign, which means the server computes a reference mode update. So this is a key idea of our defense. So next, I want to use one example to illustrate our proposed FR trust. So for simplicity, we assume we only have 2 clients. These 2 clients have local mode updates .w1 and .w2 inserted training round. And the server mode updates, so this is a server mode updates .w. This graph shows these 3 mode updates. So our intuition is that if a client's local mode updates deviate substantially from the server mode updates, then the local mode updates may be from a malicious class. So for instance, in this case, the local mode updates .w2 deviate substantially from the server mode updates .w0. So the local mode update .w2 may be from a malicious class. So based on this intuition, we compute the cosine similarity between a class local mode updates and the server mode updates, and we fed user redo to clip the cosine similarity to get the trust score for the class. Here value is a nonlinear function which computes the maximum of 0 and the input x. So in our example, for client 1, we first compute the cosine similarity between local mode updates .w1 and server mode updates .w0. Then we use redo to clip C1 and produce a trust score TS1. So because of cosine similarity, C1 is positive, so the trust score TS1 is equal to C1. And similarly, for client 2, we compute the cosine similarity between .w2 and .w0, and we fed use redo to clip C2 to get a trust score TS2. Because the cosine similarity C2 is negative, so the trust score TS2 becomes 0. So I recall that in local model point time, local model updates from malicious class often have large magnitude in order to dominate the impact of local model updates from benign class. So therefore, we also normalize the magnitude of class mode updates to further reduce the impact of local mode updates from malicious class. So for example, .w1 bar is a normalized local mode update for client 1. .w2 bar is a normalized local mode update for client 2. So finally, the server uses a global model update .w as the average of class normalized local mode updates weighted by the trust scores. And the server uses a global model update .w to update the global model. Here, beta is a learning rate, .w is a global model update. So this is a key idea of our trust. So as theoretically, we show that under some assumptions, for arbitrary number of malicious class, the difference between the global model learned by FR trust and the optimal global model under low attack is bounded. So this is a theoretic result of our FR trust. So the more detail of our theoretic result can be found in our paper. We evaluate our attack on multiple data sets. So in the following, I will only show you the results on MNIST data set. The results on other data set can be found in our paper. So again, we assume there are 100 class in total, and 20 of them are malicious. We assume the server has 120 examples, and these 120 examples are sampled from the MD dataset uniformly and random. This table shows the results. So each row means a FIR method. Each column means no attack or existing attack. So the value in the table are the testing error rate of the global model. So here, from the defender perspective, the smaller the testing error rate, the better the defense. So because we propose a new defense, so we want the error rate as small as possible. This column means all clients are done, and there are no malicious clients in the system. This column means the attacker flips the labels of local tuning filter on the malicious client. So this is a standard label flipping type. It's also one kind of data pointing type. This column means the attacker corrupts the malicious local model based on the from aggregation rule. This column means the attacker corrupts the malicious local model based on the trimmed mean aggregation rule. The last row are the testing error rate of our proposed FIR trust under different type. As we can see from this table, our FIR trust is robust against different types. So in particular, the testing error rate of FIR trust under different types are similar to the testing error rate of Federated under low type. So because that Federated is a state-of-the-art method under low type settings, which means our FIR trust is robust against a different pointing type. So recall that in part 1, we formulate our local model pointing type as this optimization program, which is applicable to any aggregation rule. So therefore, attacker can cross a W type to FIR trust by replacing the aggregation rule A with FIR trust in this formulation. So this is how we consider the W type. A W type is also called the worst attack scenario. This figure shows that our FIR trust is also robust against such a W type. So here, the x-axis is a fraction of malicious clients. The y-axis is a testing error rate of the global model. So this curve means Federated under low attack. This curve means FIR trust under the strong W type. And we can see from this graph, FIR trust under a W type and Federated under a low attack achieve similar testing error rate when up to 90% of clients are malicious. So to summarize a little bit, we design a new dynamic robust method that is robust against different pointing types. So which means the server can improve the security of federated learning by conducting a small and validation data set to establish trust. So this is part 2 of today's talk. So in today's talk, I mainly covered 5 topics, including what is federated learning, why federated learning is vulnerable to pointing type, existing dynamic robust method, how to attack the existing defense, how to defend against our proposed local model pointing type. So my research in secure federated learning not only has a huge impact on the security community, but also we see considerable interest from the machine learning, networking, and system communities. So motivated by our research, so researchers from both academia and industry are paying more and more attention to the security issues in federated learning. So this is the impact of my research in secure federated learning. So in the end, I want to briefly introduce the author of my research. So when we talk about federated learning, we mainly refer to the centralized federated learning, where a central process is controlled by a central server. However, there are multiple limitations in this centralized architecture. The first limitation is that the server is vulnerable to the center point of failure risk. The second limitation is that in this centralized architecture, in each training round, the class has to send the local models to the central server, and the server has to send the current global model to the class. We can see that server is a communication bottleneck in this architecture. The third limitation is that centralized federated learning suffers from the trust dependency issues, which means all classes have to trust a central server. So to address this challenge in centralized federated learning, people propose the decentralized federated learning. So in this decentralized architecture, each clan communicates with its own neighbors, and every clan only has a partial view of the communication graph. So this is a communication graph, and this graph can be a random graph. So this is a standard decentralized federated learning. So in decentralized federated learning, at the end of the training process, each clan will get a final global model, and the class will get consensus. For example, if we train the system for T training rounds, so we assume W1T is the final local model on channel 1. After the T rounds, we can say that if the class with the consensus, they will get the identical local models. However, in standard centralized federated learning, class only get a single final global model. So similar to the centralized federated learning, decentralized federated learning is also vulnerable to training attack. For example, malicious class can send arbitrary local models or bad information to its neighbors. So to address the security challenge in this fully decentralized architecture, we propose a balance. So in our balance, each clan uses its own local model as a reference to check whether we say the local model is malicious or benign. And we directly prove the congruency of our balance under attacks in both strongly commands and long command settings. And this paper is submitted by the CCS 2024. So besides scale federated learning, I also conduct research on scale recommender system. So you know, recommender system is an important component of many web services, which can help users to find items they have interest. So in our research, we demonstrate that the attacker can introduce a small fraction of fake users to a recommender system, such that the system will recommend the target items to a large fraction of normal users. So recently, I also conduct some research on secure large language models. So I believe everyone here has heard about the large language models, and these models have become important tools in different areas such as technology, healthcare, and education. However, large language models have caused several concerns about the trustworthiness, including deceptive activities, copyright issues, and misleading information. So one example is shown here. So this jailbreak instruction can have a malicious purpose, such as illegal request. So to detect this unsafe instruction, we introduce the gradient safe, and this paper has been accepted by SAR this year. So a multimodal model is a machine learning model that is able to process information from multiple types or multiple modalities, such as images, audio, and text. In our paper, we show that multimodal models are also vulnerable to adversarial attack. So for example, a attacker can add a small perturbation to an image. When a user uses an encoder to decode the perturbed image, it will always generate an image as a type result. So this is how we attack the multimodal models. So this figure summarizes my research, so you can see that I first identified the fundamental vulnerability in current AI system, such as I proposed a lot of attacks attack the existing AI system. After that, I also proposed defense to reduce the impact of my attack. So besides AI security, I also work on other research areas, such as the privacy issue, fairness, and optimization in AI systems. So my foundational contribution have been centered on scale and federated learning. So I first identified the fundamental vulnerability in current learning system. So after that, I proposed defense to reduce the impact of this attack. So building among this foundation, so in the long term, I aim to develop AI systems that are not only secure but also trustworthy under various challenges. So here, this is an advertisement for me. So if any students want to look for a research mentor, so you can get in touch with me. So I have a lot of mentoring experience. So I have mentored 3 undergraduate students last year. And these 3 undergraduate students had a low research experience before working with me. But after they worked with me for 6 months, each student published 2 papers in 2 peer conference as a two first authors. So 2 students are studying Duke University this fall, and 1 student is studying at Georgia. So if you want to research, you can come with me. We can have a discussion. Okay, thank you.
Okay, now I hope our students have really enough information about Dr. Fang and his research, and obviously interesting topics. Okay, do we have any questions for our speaker today?
I wanted to ask, the FL Trust system you proposed, is it resistant to concept drift as well, or would it account for concept drift if that occurred? Like, if there was concept drift in the data, would that also be like resistant?
Yeah, so in our FL Trust, we assume the server's data set and the client data set are from the same distribution. This is the assumption.
Okay.
Yeah, if there is a large drift of our trust does not work. This is one limitation of our trust. So to address this limitation, we also propose multiple defense. Yeah, you can check my website for this new defense. Yeah. Okay.
How much so you mentioned that it can determine and exclude data sets if it has too big of a deviation.
Yeah.
But what if that's after data coming in that has a large deviation? Like what if, with the example of a client being like a self-driving vehicle, if something like outside of the norm happened, but like a 1 in 1,000 chance scenario, would it exclude that data set even though it might be pertinent to research later
Yeah,
down?
so you mean the data set is too heterogeneous.
Yes.
So in this case, so if the data set is too heterogeneous, federated learning, the framework does not work.
Okay.
So you have to use a synchronous setting.
Okay.
Yeah.
Any additional question? May I ask a question? What colleague asked, in one moment, you said, okay, we are recognizing these attackers when the vectors are big and cosine.
Yeah.
But attackers are clever people also. They said, that is how you are catching.
Yeah.
You will play the game. So if you recognize these angles, where they are, then I will try to hide again.
Yeah, so this is so usually you describe is called a W type. So this is the worst case scenario. So the attacker can blend their malicious local models from below us. We have considered this setting in our table. So this is a W type. Yeah.
Okay. So you think you made the solution, or what does it mean adaptive attack? Adapting, that means we are playing games.
Yes, yeah.
Adapting. Is that
Yeah, again, you know, tiger and defender.
so? Okay. If you and what? That should be secure environment at the end.
Yeah, so we also have to propose real time to attack the current AI system. After that, propose some defense to reduce the impact of this attack. So this is what security needs.
Thank you. Do we have any more questions? If not, one more time, thank you again, Dr. Fang, for presentation. And